Okay, here's the main equation that we need to remember. So remember this. Y is equal to the initial amount. That's how much you start with. The multiplier represents the rate of growth. Bacteria usually double to reproduce, so that would make this number a 2. But like we were talking the other day about population and it growing at 8% per decade, stuff like that. Remember, we would add to 1, or if something was decreasing, like caffeine leaving the bloodstream, that's a decay. That's decreasing, right? So we would subtract from 1. But those numbers are what goes here, and then N represents time, whether it's in hours or in years, decades. All right, so here's our formula. Assuming that we have an initial population of 100 bacteria, predict the population after 5 hours. All right, so here's my 100, my initial population. And since the population of the bacteria doubles, here's my 2, and then this is N. So to work this problem, if I have 100 bacteria that double every 5 hours, on your calculator, you have a button that looks like this or one that looks like this, and those are exponent buttons. Raise your hand if you can't find one of those. It may be instead of Y to the X, it may be X to the Y.
I think I found the arrow.
Yep, the arrow. That's called a caret.
Is it?
Yeah, it's right here. X, here's the X to the Y. Sometimes Cassie over there. Yep. You see yours. All right, so do 2 and then that button and a 5, 2 to the 5th power times 100 and hit equals.
3,200.
Yeah, so in 5 hours, those 100 bacteria went to 3,200. Okay? Now, if instead of doubling every hour like this said, what if they doubled every 30 minutes? That means how many in an hour?
60 or 40?
If they doubled at 30 minutes, let's say 12 to 1. If they doubled at 12:30 and then they doubled again at 1, in all, how many have happened in an hour? 4, right? All right, so if they doubled twice an hour, you either got 4 in 1 hour or you doubled twice in an hour. Those are the same thing, because what is 2 squared? 4. So that formula could be used if it's doubling every 30 minutes. All right, now, this just means K being positive, that just means, or K being greater than 0, means that K is positive. That's a rate of growth. The bunny rabbits, the way they reproduce, bacteria, the way it grows. Okay, those are examples of exponential growth. We're going to talk about money growing exponentially also. If you have a rate of increase or a growth, then you take your percentage, whatever it is, make it into a decimal, and add it to 1. And that's your multiplier that goes in that formula we were talking about earlier. Okay, so if it's growth, you add it to 1. If it's decay, you take your negative number. That's what K less than 0 means, is that it's a negative number. And you subtract it from 1. You take your percent, you change it to a decimal, and you subtract it from 1. Have y'all found these in your packet? Okay. Now we talk about decay. Of course, the first thing you probably think of is fossil. You know, and thinking about, I don't personally really believe in carbon-14 dating and things being as old as some say they are. But that's an example of carbon-14 dating is an example of exponential decay, the carbon leaving the body to show how old something is. Another thing you might think of is anytime we intake something, a drug of some kind, whether it be over-the-counter, prescription, illegal, whatever, you know, or just in a Dr. Pepper, we might have caffeine. Those things enter the body, they have to leave the body, but they leave exponentially, not all at one time. You know, they stay there over time, so it just leaves a little at a time. All right, I think we may have worked this problem right here. Do we need to work it again?
Is that it?
Let's see. Yes, it is. Do we need to work that problem again? You've got your initial amount. Uh-oh, I need a different color here. You got your initial amount of 248,718,301 people, and they're growing at a rate of 8%, which is 0.08. Added to 1 will be 1.08. And then they're growing per decade. And so how many decades has there been from 1990 to 2010? Two. So that per decade tells you how many you put there. So on your calculator, do 1.08, do your exponent button and 2, or you could just hit the x squared, and then multiply what you get by 248,718,301. And then round to the nearest person. Since we're talking about people, it wouldn't be appropriate to use a decimal.
Is that what I'm supposed to do?
Yeah. So, in 2 decades, the population increased from about 250 million to 290 million. All right, so, and then to do 2025, well, all right, we've had 2 decades to 2010, and now we'd have 2 more decades to 2020, right? And then, no, sorry, 1 more decade. 1 more decade to 2020, and then half of another with those 5 years. What would be our exponent?
3.5.
Did you say 3.5?
Mm-hmm.
Okay. You guys agree? Okay. Why can we call this an exponential equation? Is because we have a variable up in the exponent that we substituted in the time for, and that's why they're called exponential. All right, and then we're going to talk about a little bit about decay. The caffeine or any meds leave the body at an exponential rate. And this is an example of exponential decay. The rate at which caffeine is eliminated from the bloodstream of an adult is about 15% per hour. And an adult drinks a caffeinated soda, and the caffeine in his or her bloodstream reaches a peak level of 30 milligrams. Predict the amount to the nearest tenth of a milligram of caffeine remaining 1 hour after the peak level and 4 hours after the peak level. All right, now remember, go back and look at this page right here. You're going to take your percent of decay and subtract from 1. Okay, so what is the percent of decay? 15. So 1 minus 0.15 is 0.85, right? That's my multiplier. Think about it. If I kept 100%, let's make this make sense. If I kept 100% of that caffeine in my bloodstream, I'd never get more, I'd never get less. It'd just stay the same. That would be 100%. So that's why if something's decaying, you subtract from 1, because this is 85% left, right? On the other hand, that 1.08, my population was increasing. It was greater than 100%. It was growing. So y'all understand the adding and subtraction to 1? All right, so my initial amount was 30 milligrams. My multiplier is 0.85. And we want to find the caffeine remaining after 1 hour. And then we want to find the caffeine remaining after 4 hours. So let's just type that in our calculator. 0.85 to the first is 0.85. So 25.5 milligrams will be left after 1 hour. All right, how many after 4? rounded to the nearest hundredth. No, I'm sorry, to the nearest tenth. The nearest tenth. I have this. Y'all agree? Do that. Okay, keep it in mind, you have your formula, the initial amount, and then you got your multiplier. This is when you're going to subtract from 1 because this is decaying, and then you have time. So a vitamin is eliminated from the bloodstream at a rate of 20% per hour. The vitamin reaches a peak level in the bloodstream of 300 milligrams. Predict the amount to the nearest tenth of a milligram of the vitamin remaining 2 hours after the peak level and 7 hours after the peak level. See if you can set that up. What goes here for the multiplier? 0.8, right. 0.8 or 0.80. And then after 2 hours,
I guess I was right.
did you have one at that time? Did you get them that time?
Yes, ma'am.
Is this hard?
Not too bad.
I have a question.
Okay.
Why after 7? Never mind, I got it.
You sure?
Yeah.
Okay.
Okay. I was wondering why the number got smaller after more hours, but I forgot we were going down.
It's decreasing, right. See? Alright, let me see what you got in your packet there. I want to show you what an exponential graph looks like. An exponential function or exponential equation has a variable in the exponent. Think about you're in Algebra 1. You know, you didn't solve any kind of equation with the variable, the x, way up in the exponent. It was never there. But these, the variables in the exponent. All right, I want you to use your calculator, and we're going to fill in what these are equal to. You can probably do these on the bottom in your head, okay? But write down what you think the answers are down through here. Now, let me show you. Some of y'all have a graphing calculator. Let's say, who doesn't have a graphing calculator? Let's see, we done. I'm going to show you on this kind, so I hate for you to get confused looking on a different kind. Let's say I wanted to do 2 to the negative 4th power. Alright, so it would be, I'd do 2, and I would use my exponent button, which is down here, you know, and then negative 4. Now when I hit enter, I get this decimal, which that's good. But on a graphing calculator, there's not a fraction button. That's why I was trying to be careful yesterday, letting people borrow calculators, because if you don't know anything about a graphing calculator, it really doesn't do much good. But under here, under the math button, if I hit the math button, I have a choice, number one, to make it into a fraction. So I hit my math button and I pick number 1.
Press enter.
Now I'm going to press enter and see it made it 1/16. So this decimal and this fraction are equivalent to each other. So right here, I have that decimal, or I have 1/16. Tell me what fraction goes here. What do you think the fraction would be? What is 2 to the third? What's 2 times 2 times 2?
8.
Yeah. All right. Do you guys remember enough about exponents to remember that if you have a negative exponent, to make it positive, you just reciprocate it or flip it? Like this is the same thing as this. To make that 1 positive, I just take it down here, and that's the 2 to the first on the bottom. So if I have 2 to the -3 to make that positive, it'd be like that. So you wouldn't leave a negative exponent, you just flip it. So this will be 1/8. What do you think this will be? Yep. Already told you that one. Alright. Alright, what else do y'all remember about exponents? What's anything to the 0 power? You remember?
0.
Try it on your calculator.
Oh, geez.
Anything to the 0
1.
power. What?
1.
It is 1. It is 1. It doesn't matter what the base is. If the exponent is 0, it's always 1. Even if it's variable. Anything to the 0 power is 1. Alright, so this would be a 2, right? And an 8. This is supposed to be squared. Sorry. Let me undo that. This is squared. So this is 4 and 8 and 16. That's just a little quick review about exponents, okay? So that if I graph that, y'all remember graphing? I just want to show you what one looks like. Boy, do. Alright, -4. What was its point that with it? -4 was with 1/16.
Yeah.
Imagine, you know where half is, right?
Yeah.
Imagine if I had this broken down into 16ths. Y'all looked at a ruler before, right?
Yeah.
So I halved it. I had halves, and I halved that, and I got 4s, and half that, and I had 8, and half that again, and I had 16ths. They'd make it really small, right? So 1/16 is way down here, and 1/8 is a little bit above that, and -2 is 1/4, and -1 is 1/2, and 0 is 1, and 1 is 2, and 2 is 4, and 3 is 8, and 4 is 16. This is not a line. It's curved. Sorry, it's got a little hitch in it right there. Let me try that again. Okay, so an exponential curve is like this. This is showing growth.
Right.
It's increasing really fast. It's like if I have 2 rabbits, pretty soon I've got 4 and then 8 and then 16 and then 32, right? So it's growth. Now, I don't know how many of you guys plan on going to college and taking some beginning math, college math, but it's algebra 2. And so, in case you're ever find yourself in that spot and you're doing some graphs, an asymptote is a line that a curve approaches but never crosses. A practical application of that would be, think about, you guys own any cows? I don't think I've ever owned a cow, but we've owned sheep. And sheep are so dumb. You can have the same sheep today and give him a shot on a trailer, and he has a fit and walks off, or she, or the boys are just mean. So then the next day you say the same feed bucket, go to the same trailer, give the same sheep the same shot on the same trailer, and they still don't like it. As long as you've got what? The feed bucket, right?
Yeah.
They're so dumb. But one thing they do learn is what an electric fence will do to a wet nose, right?
Yeah.
They don't take many times to get knocked back when they're little, and oh, okay, I'm not going over there and stay back here, right? So an asymptote is like that to a graph. Think about, this is the asymptote here, the x-axis. Here it is. And it's making this curve behave. It's keeping it in this upper pasture, so to speak. It's keeping it up here in this first two quadrants. What this curve doing is it just goes crazy. Goes to positive infinity. What would be next? What would be 2 to the 5th? What's 16 times 2? 32. So next I go to 32. Double that here, what would I go to? 64. Alright, double that, what would I go to? 128. Double that, where would I be? 256. Double that, by the time you get over here to 2 to the 8th, you're already at 512. I mean, it goes fast, doesn't it? It goes quickly. But what it does on this side is it gets smaller and smaller and smaller and smaller. But it's not going to touch the electric fence. Because let me explain this to you. What power, what exponent could I put right here?
What's after 512, Miss Green?
1024.
Jesus.
What exponent could you put right here to make this 0?
Nothing.
That's good, Leanne. Nothing. There is, I don't care if I did negative 16. I mean, that number's going to be so small. If I put negative 1,000, your calculator might not even show it how small. It might give you scientific notation if you guys have been in physics and chemistry. You know about that. It would give it to you so small, but there is nothing that I could put in right there to make that 2 a 0. And that's why, since y cannot be 0, that's why this curve can't touch this line. That asymptote's like, keep off here. I'm going to keep you up into the first two quadrants. So that's what an asymptote's job is. But this is what an exponential growth curve looks like. What do you think a decay curve would look like?
Down.
Start up here and go down. Whoops, I came back up. I was supposed to get closer to the asymptote this way. So decay comes down and growth goes up. Does that make good common sense to y'all?
So it'll never be in the negative quadrant?
No. That's good. That's a good point. All right, let me find you guys something to practice these with.